Tomas Evensen, who is the CTO for Embedded at Xilinx, and he's going to share all sorts of interesting insight with us about FPGAs. Welcome, Tomas.
Good morning, everyone. So I'm going to talk about FPGAs. Just show of hands here. Who knows what the heck an FPGA is? That's quite a few people. Who knows how to use it from a software point of view? Not as many people, yeah. So being a software guy at Xilinx is obviously interesting. And what I knew about FPGAs before joining, really, the FPGA part, oh, that was for the hardware guys, right? I was more interested in the embedded processors. And we'll talk a little bit about that, but mostly I will talk about the FPGA part and how you can use both together. And the really fascinating and interesting thing that's happening right now is software guys are actually programming the FPGA for accelerators and so on. So I'll get into that a little bit here. So the reason why people are looking at FPGAs, of course, is we've all seen this before, right? Moore's law doesn't really apply that much anymore. It's harder and harder just to add CPUs. Even if you add many of them, you get power issues and so on and so forth. And the workloads, of course, at the same time are really exploding. So I think a lot of people have realized that you need specialized execution engines to be able to handle all these different loads. The problem, of course, then is, well, if you have one really specific execution engine for one task, another one for another task, well, how do you do that? Because very often you want to have mixed loads, like in a data center, for example. You can't have one specific accelerator for each task because there's so many of them. So then FPGAs as programmable hardware, is what it really is, comes in, because you can use the same board for a lot of different things. So you can even time slice it. So you use it for some acceleration first, and then you use it for other types of acceleration later on. And this applies both in the cloud. So Amazon and other people, they have FPGA servers, basically, or the cards by the servers. There's the F1 from Amazon, for example. But then also in the edge, things like driver assist, ADAS, autonomous driving, embedded vision, and so on. Lots and lots of people are using FPGAs for that. So today I'm talking about what we call Sync UltraScale Plus MPSoC. And that's a mouthful. I did not come up with the name. This is a really interesting chip from a software point of view because there are lots of moving parts, lots of stuff where you can put your code, if you will. So for example, you have some A53s. So this is really more for the embedded space. And A53s are more than well enough equipped to handle those tasks. When you want to have a little bit more oomph and for compute and so on, we put that into the FPGA part of it, right? So you have 4 of them, typically running Linux. Sometimes people put a hypervisor there and have multiple operating systems and so on. We also have some real-time cores, so Cortex R5, 2 of those. In a lot of these systems, safety and security and those things are really important. So these guys you can run in lockstep, for example, which is really important for safety. Also for real time, if you really want that low latency between the FPGA and the core and not have things like caches and so on get too much into the way, then the R5s are really good for that. You have memory, of course, GPU, peripherals. A lot of what FPGAs are really good at is really high input-output. Very often what people do, they have something coming in, maybe from an antenna or something like that, or a video stream, and then you go broad in the FPGA. You can go really broad and have really wide buses since you really design your own buses in the hardware. Right? So you can have packets coming in, for example, and then you go 256 bits wide and go through the fabric while you do your recognition or classification and so on. On some of our chips, we have a video codec. We have a couple of interesting other processor units for security and platform management. So these are triple redundant processors, are supposed to be up and running all the time, of course, right? So you put your boot code, secure code, and so on. You can put them there if you want to. But then we have the fabric. So for some reason, we can't even ourselves come up with one good name. So FPGA, programmable logic, fabric, it's all the same. It's the stuff that the hardware you can program, basically, right? FPGA is a pretty old term field, programmable gate arrays. So I don't know how applicable that is. So very often you hear these terms, programmable logic, fabric, just interchange one with another. So the question is then, all right, this fabric, how do you program that? And what is it really, first of all? So that's the interesting thing. When you ask people, what is an FPGA? You very often get really different answers depending where they come from, what kind of background. So it started with FPGAs really being, what we call the LUTs, the lookup tables, so programmable logic, your NOR and NAND gates and so on, you can program them yourselves, and then you can change that. So it's really hardware that's programmable. And then people came up with, well, we're using a lot of these guys just for memory. Let's put in some hardened memory. We actually have multiple types of memory with multi-port accents and things like that. Next thing, people started to use these for things like multiply and accumulate and so on. Well, why don't we harden that and put a lot of DSP blocks? So in some of these, you have thousands and thousands of these DSP blocks into the fabric in various places, right? So that's been the trend, that you harden more and more things, which means that you can use this for the glue logic. That's sort of what it started out. So if you have your own type of bus, or very often in industrial applications, you have different types of buses, field buses, and industrial Ethernet, and so on. So you can, with the same chip, you just reprogram how you interface with those buses, right? So that's one way of doing it. Not too interesting for a software guy like myself. But those DSPs in there, if you can really parallelize your matrix multiply or your, what we'll get into a little bit later, neural networks and so on, that gets really, really interesting, right? Other people, they knew FPGAs from simulation or emulation. So we have these really big FPGAs, and then you put like 8 of them on one board, and then you can simulate new ASIC designs. So some people, that's what they do and what they use the FPGAs for, right? So that's the interesting thing. You can use it for a lot of different things. But since it's so programmable, you can have your own buses, as I mentioned, your own data flow. It's really good for things like machine learning, where there are lots of experimentation right now, lots of new ways of doing stuff. You can sort of have intelligent memory that's serving up or your weights in a really nice way, so you don't have to go out to memory all the time. So lots of innovation happening right now around how to use FPGAs for machine learning and a lot of other things. So how do you program this stuff? Right, so it used to be that really was something for the hardware guys, and they had their funky languages like Verilog, VHDL, those kind of things, right? Interesting languages, but a little bit harder for a software guy. We tend to think a little bit more in the serial fashion. There, everything's happening at the same time, right? So you really have to think in a different way. So, but if you want to program them with that, that's great. And for some tasks, that's absolutely the way to do. What we've done over the years is adding other tools on top of it. So we added the C compiler. In the beginning, it was mostly for the hardware guys, but they wanted to write it in C, but still they had to connect it with other things and so on, and do all the glue and all that stuff themselves. So you really had to be a hardware designer to use it. But you could take your C code, it will unroll your loops and so on, and if you did things like matrix operations and so on, you can really go wide and go 100 multiply accumulates per cycle and things like that, right? What we've done later, the last few years, is then add another layer on top of it for software guys like myself. So now you can write your C code, and then you can just point to a function and say, hey, I want this one to run in hardware. If you just do that and nothing else, it will probably run. It will probably not run that great if you haven't thought about things. When you would never do something like parsing a linked list in an FPGA. It just doesn't make sense. You want to have the data concise and close to each other and things like that, right? But if you know what you're doing, it's a little bit like programming DSPs. You have to understand a little bit of the hardware underneath. But once you know that, then you can apply some pragmas and things like that. You can yourself specify, how do I want the data movements to happen? Should I use a DMA? Should I plug in a new DMA myself? And so on and so forth, right? So an example of that, so the tool that's doing that in the embedded space is called ST-SoC. And we have a similar tool for the data centers called SDXL. Kind of the same infrastructure underneath, but different use cases. Because here we're running part of the application on the embedded ARM cores and part of it in the fabric. So if you imagine a really stupid program here that's not really that great because someone forgot to initialize the matrices here. So they're doing multiply and add on something that's unknown, but hey, it had to fit on the slide, I guess. So what we're doing here is really, so this is more pseudocode, of course. So you're doing a multiply B times D to A, and these can be really big matrices, of course, right? So, and then you take, it's actually A times B to D, and then you take D plus C. So it's just a regular multiply and add, a MAC operation, into E. And then on the command line, or you can do it from the IDE, you just point to these two functions here and say that, no, I want these two guys to run in the fabric instead. What the compiler does, and it looks like a regular compiler, you have the same options and things like that, right? What it does then is under the hood, it compiles the rest of the code with regular GCC or what compiler you're using, put that on the ARM, you get an L file out of that. The other stuff, under the hood, it pushes that stuff through our HLS compiler, which is a high-level synthesis. It takes the C into RTL, which is the sort of the language of the FPGA. And then it builds all the different stuff, all the glue in between as well. So in this particular case, it's kind of interesting here, that you have to get, obviously, the first two matrices into the multiplier. There you can specify yourself if you want to use one DMA for those two, or separate DMAs, or if you just want to copy it to main memory, lots of different ways. So we have really made the data movements a first-class citizen. You can really specify outside of the code itself how you want to move the data back and forth. The compiler is smart enough to see that, hey, D is the output of one of these blocks here. I really don't have to go back to memory. I can just stream that into the adder there. By doing this, you can imagine if you have a video pipeline and you have like a Sobel filter and a corner detection and something after another, you can actually write that all in C, but all the data movement, everything real is actually happening in FPGA, just shuffling the data from one block to the next block. So it's a really interesting way of doing it from a software point of view, but let the hardware do all the hard work here. Another really interesting thing with this is, it's a little bit, when I started programming, which was back in the 70s, the compilers were not that great. So very often, even if you used like C, for example, very often, if you were a nerd at least, you looked at the assembly code and you said, hey, I can do better than that, right? You didn't do that for everything, but if it was something that you really wanted to run fast, you wrote your own assembly code, if it was a 68,000 or something like that, right? But you didn't write everything, and you still had a linker that linked everything together. So you can do the same thing here. You can start putting a lot of stuff in C, put it over there. If you're not happy with the code, you can then have someone, or yourself, if you know Verilog or VHDL, replace that part as long as you connect to the axis interfaces the right way and make that sort of a library that someone else can use. So that way you can work together with your hardware guys that knows those kind of languages and use this tool more as a way to glue things together. So then on top of that, we have added other things. So like for machine learning, for example, people are not really writing all the matrix multipliers on themselves. They're using Caffe or TensorFlow and so on. So we have interfaces from that then generates either for our data center use case or our embedded use case. And that way, it's really a nice way because then we and our partners can work on optimize the neural networks that gets output from Caffe, for example, right? So as a programmer, you really don't have to know anything about FPGAs at all. We also have a bunch of other libraries like OpenCV, FFmpeg, and things like that with accelerators in the FPGA. So from a software point of view, it looks like just another accelerator, just a library you call, basically. And that's really where we want to get to, is that for most software people, they just call a library and things will run fast. And then you have some other people that are really good at writing those accelerators into the FPGA. And that's what the tools allows you to have that separation between those things. So here's another machine learning example from one of our partners, DeFi. So this is the interesting thing, of course, as you guys know about machine learning, is that you have all these different kinds of neural networks, and there's a lot of new innovation coming, and FPGAs work really well with that because you can really design your own hardware so that it really fits to it. In this case, they have an SSD network, so that's the single-shot multi-box network. And so they're comparing that with the NVIDIA GPU, and we get 5 times the performance per watt performance. And very often, raw performance is really important, and you can get that, and you can use really big FPGAs for that. But very often, it's performance per watt, right? For example, if you have a camera in a car, you can only use like 5 watt or something like that for the camera that's front-facing. So it's really the compute you get per watt that's really, really important in many cases, right? So as we heard 2 days ago, what we're doing now is that we're launching a board called Ultra 96 that will sell for $249. And this is really the first time before. Our boards that we've been providing ourselves have been bigger, really showcasing the FPGAs with all the I/O and so on. This is really meant for software guys to experiment and work on. And it's really cool. I really love this board. I've been using it quite a bit myself. And you can use it in many different ways. You can use it like a Raspberry Pi kind of like thing. You just connect to it either over wireless, or you can attach a monitor and a keyboard, and then you just do GCC and you do your make and everything on the board itself. Really easy to get going, and lots of examples and so on. Or you can download our cross-compilation tools, our cross-environment, and then you get the full Eclipse IDE where you can do debugging over JTAG and things like that. And all those tools are available for free there. What we also have is the SD-SoC tool. So that will come in a couple of months for this particular board. It's not ported to this board as of yet. But then when you get this board, you will get a 1-year free license for that SD-SoC tool as well. So this is really fun to play around with yourself, because you can, as a C programmer, C++ or OpenCL, you can write your own code and see what heck happens, and really fun to play around with. And since it's so fun to play around with, we're actually going to give away 30 of these on Friday. So we're having this contest coming up, so I really encourage you guys to look into this. So what we're going to do, you can come to our table on Friday, come up with a proposal on, hey, this is what I would use the board for. And then we'll pick the coolest ideas there, 30 of them. And then you have some time to work on it, right? And then you can submit something later on, and there will be prizes and so on for that. So kind of a fun thing as well, but we really want to get this board out for people to really experience the FPGAs, because it is a little bit of a new way of thinking, of course. So I'm going to end with a little demo, so if you guys can get that up, and it's still running. You never know when you're up here. So what are we doing here? So this is yet another type of network. This time it's a binary network. Binary means that all the weights and the activation function are just a 1 or -1, basically. So only have the 2 values. And as you can imagine, one of the advantages with an FPGA is that you can have this mixed precision. Obviously, you can do 32-bit stuff. You can do much bigger. You can do 8-bit. You can do 1-bit. It just means that it uses a lot less of these LUTs and the DSPs that's in there, and that the power consumption goes down dramatically, of course. The nice thing with binary network is that you can use bit operations instead of multiply, right? You do the XORs and stuff like that. So it's kind of interesting. And that way you can have deeper and bigger networks and get similar precision as opposed to a regular network. What we're doing here, we programmed this with road signs. For some reason, German road signs, because there was a database of that. So we put that through training in Amazon. So people always ask. So it cost $7.78, I guess, to do the training for this thing. And And then we take the output of that, convert it into a binary, the weights and so on into binary, and then we run it on this little board. So this is the board that we are, Ultra 96. It's one of these small ones that has the same, it's the same form factor as the 96 boards, of course. And the performance is pretty amazing. We are actually running in parallel on the CPUs. And again, binary networks are not that great for CPUs, right? So it's a little bit of an interesting comparison here. But what we actually get is like 19,000 frames per second. Actually, right now here, I see we get like 14,000. So I don't know if the electricity is a little bit weaker here in China or something going on. But say 15,000 here, while we get 94 frames per second on the, or tiles per second, 2.2 tiles per second, I mean, which means that it takes 92 seconds per frame to run it on the CPU, and you can do 94 frames per second on the FPGA. So then you do the calculation. So when we ran at that time, it was 8,600 times faster, which is a big deal, right? It's a pretty big deal. And so what it's doing is and then we went out and took a bunch of photos, and we're running through that. And I'm told that it actually has a couple of errors in here. I haven't really been able to detect them, but some of our guys say that there are a couple, you know, how it works with neural networks, you don't always get it right. If you want to know more about the stuff I've been talking about and are interested to go a little bit deeper, then Glenn is going to make a couple of presentations here. So one is today at 4 o'clock, talking more generally about accelerating things on an FPGA, and then more talking about the neural networks tomorrow at 11, right? So I don't know, do we have time for maybe a couple of questions?
Yes, I think that we do. Does anybody, any questions for Tomas? Mad Dog?
Not so much a question, but one thing you didn't really point out is that the FPGA not only speeds up the calculations, but offloads the main processor from having to do it. So your main processor can be concentrating more on other things.
Exactly. So one of the whole ideas, and that's something you can do with these tools as well, is to really make sure, part of it to get the speed up is to get the pipelining going so that you feel the FPGA with doing stuff all the time. But then, of course, you have then the processor free doing other stuff. And Glenn will talk more about that in his sessions as well. Good comment.
Anyone else? Oh.
Anyone here?
How much time have you spent on streamlining the feature detection process whilst creating a model, the machine learning model?
So how much time do you spend to
Have you managed to streamline the process of feature detection when creating your machine learning model, say, for image classification?
Not sure how much time we spent or how much...
Have you been able to, because a lot of time, in part of the machine learning models, a lot of effort is spent into feature detection, actually defining what features you're looking for.
Yes.
So I was wondering if you have managed to streamline that process, or that's
all right,
still...
now we get, sorry, it took a while to, yeah. I mean, the interesting thing here is that the training, really, you do that the same as with any other, right? You use the cafe and so on, you run it on Amazon or other servers to do that. So that part we haven't really changed at all. It's really the inference, the actual execution of it that we are accelerating more at the edge in this case, or in the cloud as well. So, but the training part, we're not touching that really.
I see,
yeah.
okay.
Yeah, good question.
Anyone else? Yeah.
When you provide all the standard acceleration libraries like the FFmpeg or other blocks, do your customers have to write custom drivers for every application, or is there a bunch of drivers that you provide and that you have upstreamed?
Yeah, no, so what we're doing is if you're using like our OpenCV libraries or something like that, right? So that comes, so from your point of view, so those are in open source, so you can go and see, and they're written. So for example, the neural network, binary network for this is written in C actually, so you can look at the code and see how that looks like. And then for interfaces and so on, the tool will take care of the interfaces. So what you basically do is saying that I want to have this library and this library, basically calling those libraries. And then it will create the bit stream, which is the FPGA, and the interfaces will automatically be created. If you want to, you can then go in and change the default to something different if you want to have a different DMA or have multiple DMAs so that you can stream a little bit better. But so typically the flow is that you get it going first, so you just compile and get it going. Then we have tools, and we'll talk about that a little bit later in the other sessions, where you can see exactly where you spend your time on the buses and so on, so that you can go back into your code and change a little bit so you can really streamline, so you overlap the transfer of data with the compute of data and things like that. So that's really what you spend your time on when you use these kind of tools to get it faster.
Sorry, so since your application scenario, you mentioned a lot about neural network inference scenario. And in today's a lot of inference engine, they use the standard libraries like gymloP. So the one thing I didn't quite get is, do you expect us just compile that gymloP and then your cross-compiler do that, or you have prepackaged some of those somehow we just link?
Yes, so we have, so for example, for Caffe, and we're coming up with TensorFlow and so on. If you're using those, we are doing all the, everything underneath. So we're taking the output of that and then doing all the work to get it into an efficient bit stream. And then we have roadmap of other libraries and frameworks that we're going to support going forward. So the intent is not that everyone should implement that by themselves. But still, it's fairly early on, so it's just the most popular ones that we've done. And then we have partners that's doing a bunch of the other ones as well. So there are quite a few out there already, some that we are doing, but then we have some partners doing it as well. Or you can also, of course, feel free yourself to do the lower level and experiment with that as well, because there are different ways of how you want to get the data through the FPGA and so on.
Yeah, let me just probe a little bit on that same line. When I accelerate the inference, I could just accelerate one particular operator in the network, for example, COM2D or accumulate add, or I could really extend and make it powerful to take, for example, doing inference on the whole graph. Do you have any, which approach you're thinking, which is the best way of using your engine for that? Yeah,
so currently what we're doing is actually you sort of design your own network and you use one of these frameworks, and then we take care of that. We are not really at this point helping you decide if it's better with a binary network or with a different kind of network. That's sort of up to you at this point.
Okay, thank you.
Okay, so I have one final question I'm curious about, and I think it's an easy one. So I'm just curious, are Spectre and Meltdown a risk factor in the world of FPGAs, or are they really not a consideration?
Now, that's the nice thing with FPGAs. So they are really nothing like that in there. If you vulnerabilities like that really is more an issue when people know when using the same thing. So we have ARM cores in there. On this one, we have the A53, where Spectre is not an issue. FPGA fabric itself, you can put processors there, and we have our soft cores. They don't have those kind of issues. But the rest of the code is really your own code. So if you have vulnerabilities, well, first of all, the person trying to attack it has to know what the heck you were doing in FPGA. So that's a big, because they can't easily get to the bit stream, right?
Right, thank you. All right, Tomas, thank you so much. That was really interesting. Okay, so we're going to take a little break. We'll start again at 10:30 in here for Enterprise, HPC, and AI Machine Learning, and Ecosystem Day, and next door for Automotive, Mobile, and Embedded. So have a great day, and we'll